input f of t for t is less than or greater than t naught, t0. So a system where the output at any instant t0 depends only on the value of input f of t for t is less than or equal to this value, which is t0. So such system is called causal system. What about the non-causal? Non-causal system. A system, of course, you can guess, that violates this condition, the above condition. It's called non-causal systems. But in practice, any practical system, hold on, please. Okay. Any practical system that operates in real time must necessarily be causal. So any practical system like robots or drones or smartphones that operates in real time must necessarily be causal, okay? In practice, our system is basically, we call it causal system. Okay, let's give an example how it looks like a causal system. Example. So let's assume my system equation is given as follows. Sorry, the output. Y of t is equal to f t minus 2 plus f t plus 2. So in other words, causal system it only depends on the past and present samples. In other words, it doesn't depend on the future samples or inputs. Such system is called causal system. Let me give you an example. Let's analyze this system together. In this case, assume that my input is a square signal from 0 to 1, the duration, and the amplitude is equal to 1. This is my f of t. And I apply to this system, which is this system, and the output, according to this equation, the output signal is gonna looks like what? Now it's time to use the knowledge that you learned, guys. Remember t minus 2, ft minus 2 is a time shifting process, right? Y of t, t.
So from minus 2 to 1, it will be 1, and then from 2 to 3, it will be also 1. The rest is 0, right?
Yeah, exactly. So the first sample is gonna come from shifted version, as you said, 1, 2, 3. So let me write down this way. -1, -2, -3. And this is 0. So as you said, this ft minus 2 is gonna, originally it was here, right, f of t. If we shift by 2 to the right, is gonna, because originally it was 0, if you shift by 2, it's gonna come here, right? So that's the first part, which is f t minus 2, right? But the system also shift to the left and add them up. So now it's going to shift to the left by 2, which is going to be something like this, right?
Yes.
So by 2, by minus 2, okay? This how this system is going to modify your input signal and come up with the output. So this system by itself is a non-causal because it depends on the future sample. So this negative side, we call it future. If it's exactly on top is present, and then the rest of the is past. So in this case, this is the future part, and this is the past part. So we said that the causal system does not depend on the future samples. That's why this system is non-causal. But the question is, we need to implement or realize this system in the practice. So one solution is,
I didn't understand why is it non-causal. Can you please explain that again?
okay, simply the causal system only depends on the, it doesn't depend on the future samples, okay? If there is at least one samples from the future, then such system is called non-causal, okay? When we say future is the one on the negative side, this side, okay? On the left side. So because of this part, this system is not causal, is a non-causal basically. But the important question is, we need to realize or implement this in a processor, this system, okay? So on the other hand, the practical system must be causal. So the question is, how do we convert a non-causal system into a causal system so that we can implement or realize in practice, okay? So the answer for that is non-causal system can be realized or converted into the causal or converted into causal system by using shifter, as your friend says, by delay or shifter. Let's do it together. How do we achieve this? How do we achieve this conversion? Okay, my original system, which was non-causal, y t was equal to, if you shift the input signal by to the right plus pi to the left and then add them up. That was non-causal. Now I need to convert this into the causal system using the delay or shifter. So
Yeah,
in order
maybe we
to
just put the entire system into like another -2. Would that work?
exactly, yeah, you shift My new output is gonna, let's call it y hat of t, is simply is the shifted version of this system by 2, because in order to get rid of this future sample on the left. So if we apply this shifter, it's gonna be ft minus 4 plus ft. Now I get rid of this feature. I have only the present sample and past sample. So by using a shift, like visually something like this, is a delay by 2 or a shifter by 2. This is my y of t. Now the new one is y cap of t, right? Which is the shifted version of this by 2. So now it becomes causal system. In order to implement this system in practice. Okay, we're gonna now learn a lot in the future, but this is just to give an idea, since this is the first chapter. Okay, the important things is that you should know is the causal, what's the definition, what's the non-causal systems. That was the first, the third classification of the systems. Okay, the last topic for today is an example, actually to show you how we apply this knowledge that you're going to learn in this course to a practical system in order to analyze them, basically. So which we are going to call system model. System model is actually, it shows us the input and the output description. Okay. Any kind of system you can consider, like electrical, mechanical, hydraulic, acoustic, and electromechanical, or chemical, any kind of, etc., you know, any system. We basically use this kind of tool, or the mathematical tool that you're going to learn in this course, to analyze it, okay, in a simple way. Otherwise, it's really hard to analyze and model such systems. So you need to come up with a simple kind of expression that shows the characteristic of a given system. And this system can be electrical, mechanical, computer, hydraulic, acoustic, electromechanical, chemical. In other words, it can be a robot, it can be a drone, it can be a smartphone, and so on. We need to model such system in order to analyze, and at the end we need to come up with the system expression. Okay, to show you just an example to give an idea, I'm going to show you a simple, of course, system. How do we come up with a model or analyze such systems? So I'm going to give an example from the electrical engineering example. An electrical system, which is very popular, RLC circuit again. It was LR, now is a RLC circuit. I'm sure you guys heard about this RLC circuit, right? In your circuit.
I didn't know that RLC is different from LCR or something like that.
Yeah, so let me show you them. This is a system that you can find in many electronic or computer system basically. And this is the inductance. This is the resistance. And this is the capacitance, capacitor. Okay, so, all right, I'm gonna erase it and redraw it, guys. Okay, that was the input voltage. That's the inductor. This is the resistor. This is the capacitor. And this is the output. Plus minus 1 Vc of t. And this is the f of t input. And this is y of t, basically our current. So let's assume that the inductor is 1 Henry, resistor is 3 ohm, and the capacitor is 0.5 Fahrenheit. Sorry, Faraday. Okay, this eventually is a system where the input is an f of t and the output is a y of t, which is current. Right, guys? Can you see that? Think of like a box, something like this. Okay, this is the input f of t, and this is the output that you can take it from here, y of t. This is y of t, okay? We can consider like this, right, guys? Input is an voltage, output is the current y of t. Yes? Any question?
No, I mean, yeah, sure, I can see it now.
Okay. This is one of the most popular circuit that you can see in many electronic and computer system, okay? Which is called RLC circuit, okay? Now the question is, can you show me the model of this system? Or in other words, system function of system equation of this, the equation of this system. So can you derive the system equation, the equation of this system basically? How we're gonna do that, guys? Any idea? So you're gonna come up with an equation of this system, which we call system model. It shows the relationship between the input and output. Okay, solution. Let's solve it together. It's very simple. You're gonna see it, you know, it's very simple. If you know this course, the knowledge that you're gonna learn. So we first apply the Kirchhoff. You guys know Kirchhoff voltage law?
The one that says that any 2 points can, like, the right side and the left side have the same voltage.
Yeah, so the total voltage is actually between this point is equal to f of t, right? And this f of t total is equal to this voltage, which is VL of t, right? Plus this voltage, which is VR of t, right? Plus this voltage, which is VC of t. Very simple, right? Voltage of inductor plus voltage of resistor plus voltage of capacitor. And this must be equal to the total input voltage, which is F of t, right? So according to the Kirchhoff voltage law. How do we calculate the inductor voltage? Any idea? It was the inductance times. In this case, the current
I
is
times L, wasn't it?
H times dy of t. In this case, dy is current, right, guys? Current.
Ah,
Plus, what about the resistor? R times current,
dy over
y of t, right? And the capacitor, it was 1 over c integration from minus infinity to t, the current, the integration of the current, basically. This is how we calculate the voltage of a capacitor. So that was for the inductor, that was for resistor, and that was for capacitor voltage. And this is equal to the input voltage, which is F of t in our case. Okay. So let's remember this one. In this, according to circuit theory, F of t is the voltage, V of t, and the output is current, I of t, right? Are you guys with me?
yes, we are.
Okay. Yeah. So just simple voltage law. And then I'm going to apply a differential to this equation. Then it's going to be second derivative of this, right? H times d square y of t dt square plus, right? R times dy of dt plus the differential of integration, it cancels each other. So you just come up with 1 over c times y of t equal to df over dt. So in order to get rid of this integration, I take the derivative of this equation. You guys see that? Okay, so now
Yes.
let's plug in the values together. The inductor was 1 times, right, 1 Henry, d square y, t square plus. The resistor was 3 dy over dt. And capacitor was 1 over 0.5 y of t equal to d of f dt. Now let's rewrite this. It's going to be dy square dt square plus 3 dy over dt plus 2 y of t equal to df over dt. So I can write down this d over dt in our course is gonna be a linear operator which we call d. Okay, so it's something like d square, right, plus 3d plus 2 times y of t is equal to d times f of t. So we come up with the model, as you see, guys, very simple way. So this is my system equation that I'm looking for this circuit. Can you guys see that, how simple it is?
Yes.
So this is my system equation basically. If I wanna model this system, it's gonna looks like this basically. D squared plus 3D plus 2 times y of t is equal to df of t. In this case, the input is f of t and the output is y of t. In the circuit theory, that was the voltage and that was the input I of t. So I modeled this system and analyzed it, come up with the equation that represent my system basically. Okay, so you're gonna learn this kind of stuff in this course basically. So that was the end of the chapter 1. And so I'm not gonna start the chapter 2 this week today. So that's all for this week then. So we just start with this, the fundamentals of the signals and system, their classification, their definition, what are the useful operations and, you know, kind of useful functions that we use. And then we move on to the classification of the systems, such as linear and nonlinear and time varying versus time invariant, causal and non-causal, then the system model. Then we are done with these fundamentals. Now you guys are ready to move on to time domain analysis. So we just warm up and we are ready to move forward. Okay, any question?
Hocam, will there be class tomorrow?
No, we just said it's from 1:30 to 3:30, right?
Okay. Okay, thank you, sir.
So that's
To
all.
4:30.
Sometimes we're gonna do from 2:30 to 4:30. It depends on my schedule, okay? Because at 1:30 to 2:30 there are some senior design project, bitirme projeleri. In some weeks, maybe 2 or 3 weeks throughout the semester. So in those weeks, I'm gonna start at 2:30. I'll let you know ahead of time. That's why you should allocate from 1:30 to 4:30. Okay.
Okay.
But I'll try to.
I thought instead of a third hour on Thursday, we'll be doing 3 hours today.
Yeah.
That was
so
my
I'll try to finish within 2 hours in block. Okay.
Okay. I see.
But sometimes it's gonna shift. It may shift to the 4:30. Okay. Any other question?
Right,
All right. Thank you guys, and see you next week. Take care.
I see you, sir.
Have a nice day, sir.
Bye. Oh, by the way, so after each chapter, I'm gonna put these lecture notes on the Teams, okay?